one we are going to take a look at is inductors. Okay, so for the inductors, I'm going to skip a lot of the proof that we did, and then I will just normally write the formulas, especially when we come to the series combination and then the parallel combination. With inductors, it's actually straightforward, and we treat inductors just like resistors, so you don't have to worry too much about for the inductors. So let's come here and we are going to take a quick look at inductors. So the inductor is also a passive element, but unlike the capacitor, which is designed to store energy in its electric field, for the inductor, it stores energy in its magnetic field, right? So an inductor okay, so it's designed to store energy in its magnetic field. I'm going to try to, so if you have, let's say a core material, I'm going to try to sketch something. I'm not very good with sketches. So let's say we have a core material. Okay, so this is like a cylinder. And then we have a couple of wire wound around this cylinder. Let's choose a different color here. So let's say we have one of the terminal here and then the other terminal here. So normally it's more tight than this, right? So that will be the length. So that will be the length. This will be there because the wire is round around this cylinder, right? This will have it will give us the cross-sectional area. So that will give us a cross-sectional area of the winding, right? Because it's one across that one. This, whatever material is this, is known as the core material. And we are going to be trying to find the permeability of that one. So we have that, and then how many turns? So here you can actually count 1, 2, 3, 4, 5, 6, right? But in a normal inductor, you normally have a lot of turns, right? You have a lot of turns. So this is going to give you the number of turns, okay? Number of turns. So the number of turns of the wire as you go around the core, right? You go one round, one full one is 1 turn, another full one is another 10, and so on and so forth. So this number of 10 is just basically n, okay? So with this information, right, with this information, we can find the inductance, okay, which is the property of an inductor, okay? Let's define that, and then we can write the formula for that. So the inductance, So this is a property of the material where the inductor will oppose to the change of current flow, right? So Okay, and this is measured. So basically, the inductor will exhibit, okay, opposition to the change of flow of current. So if you have a material which you try to oppose the change of flow of current, okay, then that material has some sort of inductance within it. If the material will allow the change of current, to very easily and very quickly, then that material basically has no inductance within it, right? So you have the property of inductance in the material if he has the property to oppose the change of flow of current. Because of that, okay, because of that property, if and for an inductor, current does not change instantaneously. Why? Because the inductor is going to oppose that, right? The inductor is going to oppose that change of current, okay? So in an inductor, current does not change instantaneously. Now, if you force the current to change instantaneously, then there's going to be a consequence, and we are going to see, right? You are going to have a very large voltage spike, which is very similar to the capacitor, right? Where voltage in a capacitor cannot change instantaneously, or is not allowed, because if it does or you force it, then you are going to have a very large spike of current. Okay, so that's the inductor. Okay, and that's the inductance. The property of any material, which is normally an inductor, to oppose the change of flow of current. Okay, so that's the inductance. It's measured in Henry. So this is measured. It's measured in Henrys, which is H, right? And the units can be Henry. So the units can be Henry. That's Henry. You can have millihenry, which will be times 10 raised to the power negative 3. And you can have microhenry, which will be times 10 raised to the power negative 6, just like the farads in the capacitor. Okay, so now that we've defined an inductance, right? So what is the inductance of this material? What is the inductance of this inductor? So what we have over here is an inductor. Okay, what we have designed over here is an inductor. What is the inductance of this inductor? The inductance is given by so let me go up, and then I'm going to show an arrow which is going over here. The inductance of this material is given by the number of turns squared. Okay, the number of turns squares. We have the permeability of the core material that we are using. Okay, the permeability of the core material. We have the cross-sectional area, and then divided by the length. Okay, divided by the length. So that will give you the expression if you actually physically design this inductor, right, to be able to compute what the inductance of that inductor is, okay? The voltage current relationship for the inductor. Voltage current relationship. So for the inductor, we have V, the voltage, to be equal to the inductance multiplied by the first derivative of the current. Okay. So if you remember, for the capacitor, we have I to be equal to C divided dt, right? For the inductor, that is what we have, right? The voltage is equal to the inductance multiplied by the first derivative of the current, okay? Okay, therefore, if you want to get the current, so similar, then we have to integrate, right? So this implies that for the current, this is going to be 1 over the inductance. We have to integrate the voltage, the T, and hopefully, if there is some initial current flowing through the inductor, then we have to take that one into consideration. So if we need to find the current which is going through an inductor, then we have to integrate. Let's get this color here. So that is the current voltage relationship. Voltage, we differentiate the current, and then for the current, we integrate the voltage. What's the energy stored by an inductor? Okay, so I'm not going to derive this one here. So this one, we are going to energy stored. For the capacitor, we derived it, right, in an inductor. So energy stored in an inductor, very similar to the capacitor. That energy is equal to half, right? Just like the capacitor. L, capacitor is a C, and this time is the current squared, right? Is the current squared. So it's very similar. Half L I squared. The energy for the capacitor is half C V squared. Okay, half C V squared. Okay, so those are the three important initial relationships, okay, that we need. And what's the last one we did with how the inductor behaves in a DC circuit? Okay, how does the inductor behave in the DC circuit? So how the inductor behaves in a DC circuit. So we did that for the capacitor. So we know that for the capacitor, the inductor is an for the capacitor becomes an open circuit. Okay, so in the DC circuit, right, in the DC circuit, so I'm going to put some inductor here, and because we normally deal with current, so let's assume this is current, and let's assume this is an inductor. Okay, I'm going to put a resistor in there. Let's put a resistor in there. Okay, so that's what we have, right? And let's assume the current is constant. Okay, let's assume the current is constant. Okay, so if the current is constant, so that's a constant one. So we have current which is coming here. Okay, DC circuit, that's R, and that is L. Okay, the question is, what is the I dt? Okay, what is the I dt? Okay, the voltage, let me use a different color for that. So we call this one V. Okay, that's the voltage V. We see that the expression for the voltage is L di dt, right? The expression for the voltage is L di dt. If the current is constant, right? If the current is constant, so let's put this one here. If which is a DC, right? That is DC. Then the I dt is going to be 0, right? If the current is constant, then the I dt is going to be 0. What does it mean? It means that the voltage, which is L di dt, will be 0. This implies that the voltage, which is L di dt, is going to be 0. If the voltage is 0, right, the voltage of an element is 0, right, then it means that that element is shorted, because when you have an open terminal, the voltage will not be 0, right? So far as you can do a KVL across an open terminal, that voltage is not going to be 0. The voltage for sure is going to be 0 if it is shorted, right? As an example, when you have an open terminal, and this is, I think I'll have to go all the way up, but I just want to show you the example we just did for the capacitor. I think is a capacitor example, this one, right? So this V1 is an open circuit. Capacitor is open, right? Open circuit doesn't mean the voltage is 0. Yes, we calculated it and we had a voltage, right? V1 was 9 volts. Yeah, so open terminal, and we have a voltage across. So far as there's current flow in the circuit, when you have an open terminal, there's going to be a voltage across it. For the voltage to be 0, it means it has to be a short. The resistance has to be 0. right? The resistance has to be 0. Therefore, if the voltage across that inductor is 0, because the current is constant, right? If the voltage across that inductor is 0 because the current is constant, this implies that, okay, inductor acts like a short circuit. Okay, the inductor acts like a short circuit. Okay, so that's basically what it means. It means that this circuit here is equivalent, right, to that, and this behaving like a short circuit. That's what it means. If this is DC and if this current is DC. So the inductor will behave as a short circuit, right, in a DC circuit, and we know the capacitor behaves, right, the capacitor behaves like an open circuit in DC. So those are the three things, the four basic things we discussed. Some of them we proved for the capacitor. The current voltage relationship, very important. So voltage, you differentiate current you integrate. The energy stored in an inductor, very important. So as soon as you know the current, you'll be able to find the energy. And then how you treat the inductor in a DC circuit, how you treat the inductor in a DC circuit. So let's take an example. We'll take an example, play with it before the break, right? So let's take some example. So we have the first part. I'm going to skip the example. I have some example on this one. This is like integration differentiation, right? So those one we know how to do them. Give some expression for current and then differentiate to get the voltage. Give some expression for voltage. You integrate. So those ones, you know, we've done a lot of them now, right? So hopefully, if you get it, you should be able to do it. Most important thing is that we want to keep the formula. I want to get an example where I have an actual circuit. I like a lot of practical stuff, right? So I'm going to get an example with inductors in the circuit and those things, and then we try to solve that one. And then hopefully we can take our break. Let's go ahead and take a look at this circuit. Since we've done the capacitors, now I'm combining both capacitors and inductance in a circuit because we know how to treat the capacitor in a circuit. Okay, if the source is DC. So this says find IL and VC, right? The question says find IL and VC. So that is the first part, A. And then the B part, we want to find you want to find the energy stored in the capacitor and inductor. So yeah, go ahead. Okay, so I'm going to give you some few minutes, 2-3 minutes, to see whether you can solve this. It's not very difficult. Just replace them by the equivalent circuit. So far as we know that this is a DC, this is DC, right? This is DC. Replace them, and then you can try to analyze it. As soon as you replace them with the equivalent circuit, what is left is you analyzing the circuit with any of the techniques you know. So we've done so many techniques in terms of how to solve a circuit. So use the one which is more convenient for you to solve those parameters. Okay. So let me give you some few minutes, 2-3 minutes, and see whether you can solve it. If I get the first solution or first two solutions, then we can go ahead and finish this one up. And if anything is confusing, so anytime I ask you to solve a problem, if anything is confusing, just go ahead, unmute yourself, and you can ask, or you can go ahead and type something in the chat window and I can read it. So you don't need to do both of them. If you have current, you can type it up. If you have voltage, you can type it up. I just want to make sure something is going on. Okay, let's go ahead and solve it. It looks like this is taking long. Okay, so it's a simple circuit. Yeah, it's a simple circuit. So as soon as you are able to draw the equivalent circuit right, you are going to see that this is a simple circuit, right? So we need to find IL and we need to find VC. So that's the first part. And then the second part, we just use a formula. So we need to draw the equivalent circuit. We need to draw the equivalent circuit, right? So equivalent circuit. Okay, so what happens? Inductor, becomes a short, and capacitor becomes an open circuit. So this is short circuit. Okay, so that's what the circuit will reduce to before we start to solve. So I'm going to go ahead and copy that and bring it here. So erase a few things. So that is going to go, and that is going to go, and that goes. And basically I have, okay, the inductor has to go. So inductor is replaced with a short, capacitor is replaced with an open circuit. So that's the circuit we have. All right, that's the circuit we have, okay, by just doing the equivalent circuit for the inductor and the capacitor. So if you look very closely, what is IL? IL is a current flowing in this part. Now, because this is open, no current flows through that, right? So it's open circuit, I is equal to 0. So I can actually remove everything. I can actually remove all this and remove all that. And you are going to see that VC is the same as the voltage across the 1 ohm resistor, right? VC is the same as the voltage across the 1 ohm resistor. And what is IL? IL, because no current is flowing through here, the current which is going to go through this resistor is also equal to IL. So IL is also the current which is flowing through the 1 ohm resistor. Okay? IL is the current which is flowing through the 1 ohm resistor. So this circuit here, if you simplify it, right, this circuit over here is equivalent to having our current source. We have this resistor in parallel, and we have this 1 ohm resistor, and voltage here is our VC, and current here is our IL. That's the circuit we have, right? And then this one here is 4 amps, and this 4 amps is coming and is going to split into these 2 branches. That is 3 ohm, and that one here is 1 ohm. Let's put a 3 ohm on this side. So that's the circuit we have, right? So this is the simplified version of the circuit, right? So you see that IL, because you have current coming in, right, and splitting between the 3 and the 1, right, you can do current division. You can do current division to find IL, which will be the current flowing through the 1 ohm resistor. And then when you know that current, then you can use Ohm's law to find VC, because VC is also the voltage across the 1 ohm resistor. Okay. Okay. So we can say here that let's solve this one now. So hopefully everything is clear now. So we can say using current division, right? We can say that RL. So if we're interested in the current here, what is going to come on top of the formula is going to be the resistor in the opposite branch. Okay, don't forget that. So IL is going to be equal to 3 over 3 plus 1, and everything multiplied by the current, which is going to be 4. And when you do that, you get 3 over 4 times 4, which is 3 amps. Okay, so that's IL. And then how do you get your VC? Ohm's law. Okay, so using Ohm's law, okay, you know VC is going to be equal to I times R, right? And this is going to be IL times 1, and this is going to be 1 times 3, and this is 3 volts. So VC is equal to 3 volts. VC is equal to 3 volts. Okay, I'm going to try to keep all the solution on this page. So like this is what I'm going to do. I'm going to draw a line over here, and then we'll do the rest on the other side because it's very small. So the energy stored across the capacitor and inductor. So let's say omega C is half C V squared, right? And this is going to be half the capacitor for the 2 farads. So it's going to be half times 2. The voltage across the capacitor is 3 squared, and that gives us 9 joules. And then for the inductor, omega L is half L I squared. So it's going to be half L is 0.25, and then the current is 3 squared. And when you do that, basically you get, what do I have here? 1.125 joules. Okay, so I just can keep all the solution on one page. Yeah, so that is how you solve this problem. Okay, that is how you solve this problem. So the main thing is first representing the circuit by the equivalence. Capacitors always become open circuit. This is if the source is DC, right? This is if the source is DC. Capacitors become open circuit and inductors become short circuit. And then you can then figure out, redraw the circuit. You know, anytime there's an open circuit, no current is going to flow, right? So you can redraw the circuit and realize that VC is the voltage across the 1 ohm resistor. So far as you can find the current, then you can be able to find that, and that current you can do current division. Any questions, comments on this particular problem? Any questions, comments on this particular problem? Sounds good? Okay, good. So no comments. So let's write out the formulas for series parallel combination, and then we can take our break. So that one is, like I said, is the same as the resistor. So inductors in series and inductors in parallel. Okay, inductors in series and inductors in parallel. We are not going to prove that. So inductors connected in series. So if you have a couple of inductors, so I have a voltage here, right? This is L1, L2, and this is Ln, right? And then the voltage across them, V1, V2, Vn, right? And we want to represent this circuit to be equal to or equivalent to just one inductor, like that. Same voltage here, and the current flowing through is the same. So if we say this current is I and this current is I, right, then this L here is basically the L equivalent. Okay, so in that case, connected in series, L equivalent is just giving us the sum of all the inductance. So it's just like resistors connected in series. Okay, so you don't have to do anything special. So in that case, you treat them just like resistors. Okay, if you need to find the equivalent inductor, you treat them just like resistors. And then when they are connected in parallel, you also treat them very similar, right? So inductors in parallel, inductors connected in parallel. So let's say this is L1, L2, Ln. We can join all of them together like that, and everything here like that. So for this one, we know the voltage across them is going to be the same. Okay, the voltage across them is going to be the same. The current is going to be splitting up. So if this is I, then that should be I1, that should be I2, and then that will be IN, and so on and so forth, right? For inductors in parallel, if I want to represent all this just by one inductor, where I have my voltage and the current which is coming here is I, just the I from the source, then this will be the equivalent inductance, and this is treated like resistors in parallel. L equivalent is equal to 1 over L1 plus 1 over L2 plus 1 over Ln. Now, if you have only two of them in parallel, then you can combine them just like we do for resistors, right? So it's going to be L1 times L2 over L1 plus L2. This is for the inductors, okay? This is for the inductors. So that is inductors in series and inductors in parallel. We do this for the resistors, so there's nothing different, okay? So I'm going to stop over here for the first section of the class. When we come, so we should be able to finish this in this first section, and we are going to start chapter 7. When we come back, we'll take one more example of the inductor, which does deal with inductor circuits alone, and then we'll try to make use of the voltage and current relationship in a circuit, right? In the circuit, in the real circuit. And then that will bring us to the end of the chapter. So we'll be able to finish chapter 6 in the second part of the class today, and then we are going to start chapter 7. Okay, so I'm going to go ahead and end the session now, and I will see all of you back here. Hopefully those who can make it back in the afternoon session at 1:30.